Welcome to Newton's method in multivariable calculus. I am Ronald Johns. What we're going to do is use Newton's method to approximate the solution to a system of equations. They might be nonlinear. F of xy equals 0, g of xy equals 0. We want to know the values of x and y that simultaneously satisfy both of these equations. Here is the problem we want to solve. Approximate a solution to these two equations. X squared plus 2y squared equals 1. 2x squared plus y squared equals 1. The graphs of these two equations are ellipses. If we look at x squared plus 2y squared equals 1, that's this blue ellipse. And if we look at 2x squared plus y squared equals 1, that graph of that is the red ellipse. What we want to do is to find this intersection point of those two ellipses. The coordinates of this point will satisfy both of these equations. So what we'll do is, since we don't know what this point's coordinates are, we'll start with a point that's pretty close to this one. How about this one right here, where the x coordinate is 1 and the y coordinate is 1. What we'll do is start with x naught y naught equals that point, 1, 1, and we'll use an algorithm for Newton's method to hopefully find better approximate solutions. We start with x naught y naught, the next approximation x sub 1 y sub 1, x sub 2 y sub 2, and so on. So let's see a little bit of the theory behind this method. Let's suppose that x sub n, y sub n is an approximate solution of f of xy equals 0, g of xy equals 0. So I'm not assuming that this is an exact solution, but pretty close to the exact solution, the real solution to this problem. How do we generate a better approximation, x sub n plus 1, y sub n plus 1? What we'll do is linearize the problem. F and g might be non-linear functions. The graphs do not have to be lines. And so here's what we'll do. A little bit of theory. Let's let delta x be x sub n plus 1 minus x sub n. Delta y is going to be y sub n plus 1 minus y sub n. Then, by using the linear approximation, f of the point x sub n plus 1, y sub n plus 1 is approximately equal to f of x sub n, y sub n, plus the partial derivative of f with respect to x at x sub n, y sub n, times delta x, plus the partial of f with respect to y at the point x sub n, y sub n, times delta y. Delta x and delta y, remember, are just the difference of the x coordinates going from x sub n to x sub n plus 1 and going from y sub n to y sub n plus 1. So this is a linear approximation of the function f at these coordinates. So then, similarly, we could say that g of this is approximately equal to this stuff. Looks exactly like the equation up here, except we have all g's. So here's the equation that we saw for f of this point earlier. And what we would like to do is to find a better approximation, x sub n plus 1, y sub n plus 1. In an ideal situation, we'd like f of this point to be 0. But here's what we're going to do. If we look at this equation up here, we could say, well, let's replace this with that linear approximation, which is this stuff. And we'll set that equal to 0. Similarly, for g, if we want g of this point, same one as we have up here, equal to 0, we could let the linear approximation of this thing, which is all of this stuff, equal 0. So if we look at this for a minute, it looks like we have to solve this equation and this equation. Well, what do we have to solve it for? Well, let's think about that. So here's what we're trying to solve now. This equation and this equation. This stuff equals 0. This stuff equals 0. Where both of these are linear approximations of f and g at the point x sub n plus 1, y sub n plus 1. In our particular problem with the two ellipses, f of x sub n, y sub n is x sub n squared plus 2y sub n squared minus 1. G of x sub n, y sub n is 2x sub n squared plus y sub n squared minus 1. And if we think about it for a minute, if we have these formulas for G and f and G, we know what f is, and by differentiating, we can find this partial derivative and this one. And for G, we know the function, we can differentiate it to get this and this. So the only unknown things here are the delta x and delta y's. So what we have here are two equations and two unknowns. And if we just rearrange this a little bit, we have this number times delta x plus this number times delta y equals this number. We just subtracted this term from both sides of the equation. And similarly with the second one, we can write it this way. This stuff equals minus g of x sub n, y sub n. So here are the two equations we need to solve. This number times delta x sub n plus this number times delta y sub n equals this number. And similarly down here. We're going to start with x naught, y naught, and use these equations to get x sub n plus 1, y sub n plus 1. And we can do that after we solve for delta x sub n and delta y sub n up here. So f of these numbers, remember, was x squared plus 2y squared minus 1. And g of these numbers is 2x sub n squared plus y sub n squared minus 1. So if we look at this, the partial of f with respect to x, well, let's see, f is right here. The partial of this stuff with respect to x is just 2x sub n, and it's multiplied by delta x sub n up here, isn't it? And then this partial derivative times delta y sub n turns out to be 4y sub n times delta y sub n. On the other side, equals minus f of this is just minus this stuff here. Similarly, for this equation, the second one, here's the partial of g with respect to x. Here's the partial of g with respect to y. And this stuff right here is g of x sub n, y sub n. So we have two equations here. And the unknowns, remember, are the delta x sub n's and the delta y sub n's. We can use algebra to do this. We can solve these two equations and two unknowns. We can do it by hand, or we could use some computer software. But in any case, it's a high school algebra problem, though I suspect most high school students couldn't use their algebra to solve these. But if they're bright, they could. So we're bright, but we're not going to solve them. Not by hand, at least. So here's a little bit of sage math code. We'll declare x, y, dx, and dy to be variables. And then we have solve. And then in square brackets, we're going to put a list. The first equation, and then the second equation, which is right here. And we're going to solve them for dx and dy. I'm using the variables dx and dy to represent delta x sub n and delta y sub n. So after we execute this cell, it tells us that dx is this stuff and dy is this stuff. So then we know that delta x sub n is going to be, according to this up here, minus this fraction, 3x sub n squared minus 1 over 6x sub n. Delta x sub n is equal, remember, to x sub n plus 1 minus x sub n. So if we solve this equation for x sub n plus 1 by just adding this x sub n to both sides of this equation, we can get what x sub n plus 1 is. Similarly, from this second one, delta y sub n is this, but delta y sub n is defined to be y sub n plus 1 minus y sub n. And so this equation right here, this stuff equals this stuff, can be solved for y sub n plus 1. So by doing that, we're going to get x sub n plus 1 in terms of x sub n. We're also going to get y sub n plus 1 in terms of y sub n. So here's what we just found. So adding x sub n to both sides of this equation, we get x sub n plus 1 is x sub n minus this fraction. And adding y sub n to both sides of this equation, this stuff equals this stuff, we just get that y sub n plus 1 is y sub n minus this fraction up there. And so now we have x sub n plus 1, y sub n plus 1 entirely in terms of x sub n and y sub n. If we had more complicated equations, we might find situations where x sub n plus 1 depends on both x sub n and y sub n, and similarly y sub n plus 1 could depend both on x sub n and y sub n. But the equations that we started with were pretty simple, and so it falls out this way. So now we can write a short Sage Math program to find x1, y1, x2, y2, and so forth. So let's see what happens here. We first set x equal to 1 and y equal to 1. My intention here is basically to set the point x naught, y naught equal to 1, 1, as we did in our prior calculations. And now, for k in the range from 1 to 10, we're going to do a whole bunch of stuff, do some calculations in these lines, and print some results here. And then when we execute this cell, we're going to get this output over here. So let's look at this a little bit more. For k in the range 1 to 10, what will happen is k will first equal 1, then 2, then 3, all the way up to 9. It doesn't get all the way up to 10. 10 is kind of a less, I guess you can say, an upper bound that we don't actually reach here. So this more or less lets k range from 1 to 9. So first of all, we have a formula. This x here you can think of as x sub n plus 1, and it's the old value of x, which we'll call x sub n, which we called x sub n minus this fraction, where you can think of all these x's as x sub n's here. Down here, y equals y minus this fraction. We take the old value of y sub n, we calculate this stuff with it, and we store it back in the variable y. But in this case, when this is executed, the new value will be y sub n plus 1. So this and this equation right here, this assignment statement, I should have said right here, calculates the n plus first values of x and y if you already calculated the nth ones. And since we started with the 0th one being 1, 1, we can use those two to calculate x1, y1, x2, y2, and so forth, just by executing this block of statements over and over in a for loop. Now, something here looks a little bit strange. N underline AP equals capital N of x digits equals 12. Let's look at the right-hand side of this first. N is a built-in function. It has two parameters. I'm giving it the first parameter of x, and I want to get a decimal approximation of that number with 12 digits. Basically, I just want 12 significant digits. A decimal, so this right-hand side converts x into something similar, the value of x to 12 significant digits, and it stores it in x underline AP. I thought x underline AP made sense. It's an approximation of x, decimal. Similarly, we will find 12 digits of y here. And then after that, we'll print the value of k, which was the loop variable up here, and then that 12 significant digit representation of x, the 12-digit representation of y. So here's what happens. X sub 1, y sub 1, when k is 1. X sub 1 is 0.6666667. I don't know if I really said all those x's. And similarly, y is this. Then x sub 2 and y sub 2 are these two numbers, 0.583333, and then we can find x of 3, x of 4, all the way through x of 9. These first numbers here are the values of k. The second numbers we have here are the x values that are printed each time through the loop. And this column of numbers here are the y values printed out. Now, if you look at this, these numbers seem to be getting closer and closer to something. By the time we get down to x of 9, we have 0.577350269,190, and the same for y. That's not surprising. Our equations were kind of symmetric in x and y. So in this case, all the way through, we happen to get the same value for x sub n and y sub n. But in general, in non-symmetric cases, the x and y values do not have to be equal. Well, it turns out that those two equations that we're trying to solve for x and y, for the basically intersection point, you can solve those algebraically, and the exact solution to the set of equations we started with is the square root of 3 over 3, square root of 3 over 3. Here's a homework assignment. Solve the system of two equations in x and y and show that one of the solutions is this. Now, the square root of 3 over 3, if we use Sage Math to print it out, is at least to, I guess, I'm not sure how many digits that is, but here it is, out to a certain number of digits. If you compare what we have down here with what we have up here, we have 0.577350260, and here we also have 0.577350269, I guess. And then over here we have 190, and down here we have 189. So this one differs, I guess you can say, in this digit right here. If you add one more to it, this part would be 190, which is the same thing that we have right here, 190. So this number is very close to what we have down here. And if we went a few more iterations of this code, maybe 1 to 15 instead, maybe we could get even closer to this. I'm not sure we would. I haven't tried it because when we do this calculation, we're not using exact arithmetic. We're using approximations. The values of x and y are calculated maybe with 32 bits, and you can only get a certain accuracy with that. So it might turn out that this last line is about as accurate as we can get, even if we went through more iterations. You might like to try this at home and see what happens if you go past x sub 9, y sub 9. But in any case, we saw that by starting with 1, 1, and using Newton's algorithm here to get successive approximations of the solution, we got points that look like they're converging to the square root of 3 over 3, square root of 3 over 3, which was the exact solution to our system of equations. I hope that you enjoyed this video. Please stay tuned for hopefully more to come. Thank you.